Should have been recording this. Okay, so now if we look at water here, right? We look at water. How many things are bonded to the center? Things. 4. 4 things are on the center atom there. Okay? There's 2 lone pairs and 2 bonded atoms. Okay? Those count. So there's 4 electron domains. So if you look at your chart, your VSEPR table, right? If you look at your VSEPR table, we've got 4 things, and then we go down over here, we've got 2 lone pairs, so there it is. Okay, it's bent. All right, bent is our geometry for that one. Right? All right, so its shape is bent, so I need to change these out. My magnet model here, and I'm going to put those lone pairs in. So now, if you look at this, is this guy polar or, well, in all the bond angles here. We'll get to the bond angle in a second, but I just want to stick with polarity for the time being. Is this guy polar or non-polar? What do you guys think? What molecule is this? You're very familiar with it. It's H2O. It's water. Is water polar or non-polar? Wow, not everybody wants. All right, I'm going to sit and wait for the answer for this one. You got to know this one. What is water polar or non-polar? All of a sudden, you're like second-guessing everything you've ever known. Just because of this silly little picture right here, I think. Water polar or non-polar? Dude, what? Like, is that gas? What properties does water have? It's like high surface tension, right? High heat of vaporization, all that sort of stuff. Polar. Water is very polar, people. Water is very polar. But you're freaked out all of a sudden. Why? How's this thing, how would you argue that that's non-polar? It looks symmetrical, right? It looks symmetrical, doesn't it? You think that's symmetrical? The picture there? Remember, it's 3D in shape, right? It's 3D. This is why you got to think 3D, okay? You have to think 3D. So, if this is ball bearing in the middle is oxygen, right? Our 2 sticks represent the bonded hydrogens. These guys are the purple ones up here are the lone pairs. Sure. Okay, look. I hold it like this. Whoop. Cut it in half like that. It looks symmetrical, right? How about now? I cut it in half, looking right at it like this. That's symmetrical. I got a hydrogen on this side. I got a lone pair of electrons on that side. Not symmetrical. That is not symmetrical. Okay? Yes.
So in this, like, realm, it has to be symmetrical in every way, not just one.
Not just one way. It's got to be symmetrical every way. Yeah. So you got to look at it and you got to think about it closely and spin that molecule in your mind there and see if it's polar or non-polar. Okay? Now, rule of thumb, okay, which means it's not always a rule, right? Some of the times. But a good rule of thumb is that if it has lone pairs of electrons, more than likely, it's polar. More than likely. But you want to, if you think it's non-polar, you want to look real closely at it, right? But rule of thumb is if it's got lone pairs of electrons on it, it is polar. Okay, but that's not always the case. But it's a good place to start. All right. Now, when it comes to the bond angle here, I would say that the bond angle between our two hydrogens is less than 109.5. Why two less thans? Why would I call it less than 109.5? Okay, so let me show you. Let me give you an example of why less than. So I'm going to come over here. We just did CH4, right? I'm going to try and draw them a little 3D-ish with the wedges. All right, so we know the bond angle here is 109.5, right? I'm going to draw another molecule with only one lone pair of electrons on there, like ammonia. All right, this bond angle right here, I would say is less than 109.5. Okay, and then with water, I'm trying to draw them with like ears to help us visualize it a little bit more and the space that those guys are taking up. Now the bond angle right here between those two hydrogens, I'm saying is less than 109.5. Okay. The actual bond angles here, 109.5 for methane. For ammonia, when we replace one of those hydrogens with a lone pair of electrons, it's less than 109.5. It's 107. I don't care that you know that it's 107. Just say it's less than 109.5. You just need to be able to make the argument that it's less than 109.5 if it was all four bonds, right? Okay. And then with water, we got two lone pairs, so those hydrogen, the bonds that are holding onto the hydrogens there, the oxygen, are pushed down even more, right? They're being squeezed down even more there, right? So that goes down to 104, it's like 104.3 degrees, okay? But I don't care that you know that number, you just need to know that it's less than, like it's much less than, with two lone pairs of electrons on there, and as comparison, okay? That makes sense? Do you understand why it's less than 109.5? Because you have two lone pairs of electrons? Okay? All right. Okay. And even for number 2 here, the hybridization is sp3 for the oxygen because there are 4 things around it. So those electrons are housed there and there, sp3. Hybridization for the oxygen. Okay? All right, why don't you guys do the next one? I'll give you a minute to do the next one while I find that. And I'll put it up here and we'll see where we're at. You want me to do one more or let you go? So I'll give you a minute. Oh. Also, as you're going through this, as you start to go through the rest of them, just FYI, I put all of them on here, so you can check all the structures you have, so you can make sure that you're looking at the right structure as you go to identify the molecular shape. Because if you have the structure drawn wrong, you're probably going to have the shape wrong and stuff. Okay, so make sure you bring up the OneNote file and look it over. All right, so let's see here, Anthony, what'd you have for the shape? Octahedral, good, yeah, 6 things bonded, no lone pairs, octahedral. So then what'd you have for the bond angle then? 90 degrees, and it's sp3b2, right? Polar or non-polar? Same polar. Same all the way around, right? No matter what you look at it, and if you want, you can always look at the table that you have in some of the pictures down below there, right? It has a picture of octahedral. When you look at that, like, all right, if I chop it up down those bond angles, is it symmetrical? And it is. Okay? We good with that? All right, so job is to finish the rest of these. Finish the rest of these. Do it to it.